Greetings, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to be discussing a topic that you already probably know a good bit about, and that is transformations and symmetry. Please copy down the title as well as the objective and your essential question. Okay, our objective for today is to acquire definitions and procedures for transformations and symmetry. The student will display the ability to perform indicated transformations and identify symmetry in provided situations. And the essential question for today, at least, will be, can I recognize and apply the various types of transformations and symmetry? Now, as you're going to see over the next several days, we're going to be using transformations and symmetry in a way that you have not used them before. But before we can get to all of that, it's obviously important that we get a basic knowledge of the terms and definitions before we move on. Anytime you need more time, press pause and then hit play when you're ready to move forward, or you can always rewind the video to hear parts that might have gotten away from you. Let's get started. Okay, now transformation. Okay, a new term, transformation. All a transformation does is it takes an object, which is referred to as a pre-image, and alters it in some way. Now, a lot of what we're going to be talking about today are the different types of transformations. There are 4 of them, and as you'll see, they do considerably different things. The new object, after a transformation has done its work, is called an image. So you have a pre-image, which is like an original object, and then an image, which is an altered object in some way. As I said, there are 4 basic types of transformations, and you are probably already familiar with the basic categories, but let's take a look. They are reflection, rotation, translation, and dilation. Now, you may have picked up some simplified terms along the way in junior high, things like rotation being a turn or a spin or things like that. That was great for junior high, but we're going to have to get rid of that vocabulary. You may have heard a translation being called a slide or glide or things like that. Going to have to get rid of that vocabulary. The stuff we're going to see in geometry, high school geometry, is obviously going to use the correct vocabulary, not the simplified stuff that you might have heard in junior high. The first 3 types of transformations in that list are what are called isometric transformations. Now, decoding that word, isometric, the prefix iso means same, and metric means of measurements. So we're talking same of measurements, same measurements. So in other words, okay, an isometric transformation does not change the size of an object. Okay, so let's take a closer look at those 3 isometric transformations. The first one would be the reflection. Okay, and a lot of people know exactly what a reflection is, even if they don't exactly know how to define it. And a definition would be a reflection bounces an image through a plane. Okay, so looking at the example, or looking at an example of a reflection, might be something like this. Reflect capital D through the line. Well, obviously, capital D and all the pieces of capital D are basically going to look into what's called the plane of reflection, or think of it like a mirror. Going to look into the mirror, and obviously it will see itself the same distance out behind the plane as it was in front of the plane. And of course, whatever was the closest to the mirror will still be closest to the mirror, and so on. Now, reflections are typically really very easy if the plane of reflection is perfectly vertical like this one is, or possibly perfectly horizontal. Okay, but reflections actually become quite complicated if the plane of reflection is slanted. As a result, you can almost guarantee that anytime we see a reflection in high school geometry, the plane is going to be slanted, the plane of reflection, and that can complicate matters a little bit. So I have a strategy for you. Now, there it is again. The original figure is called the pre-image, and the result after the reflection is called the image. Now, as I said, I'm going to give you a strategy to never ever miss a reflection, and here is how you do it. What we're going to do is we're going to, instead of trying to move the entire image all at once, kind of what we're going to do is we're going to break it down into a bunch of little pieces and move them one at a time. Okay, so to put it in Euclid's vocabulary, we're going to take this structure and we're going to break it down into its points. Okay, so let's look at the same example here again. Reflect the D through the line, thinking of it like a bunch of points instead of like a solid object. So essentially what we're going to do is kind of reconstruct the D out of smaller pieces, and then allow those smaller pieces to look through the mirror one at a time. In so doing, what we end up doing is reconstructing the object or the pre-image one piece at a time, and we end up with our image. Now again, people say, well, what's the point of that? We were able to do the capital D on the previous slide with no problem. Well, again, when the plane of reflection is vertical or horizontal, okay, it's really not that bad. But trust me, this strategy is going to be much more effective when your plane of reflection is slanted in the picture. Okay, so in that case, you're done, and you've got your reflection. Now, rotations are the second type of isometric transformation. Okay, and a rotation obviously rotates a figure. Now, something we're going to have to know about a rotation is what they want it to be rotated around. So they're going to have to provide us with a given point. Okay, it's not enough just to spin an object because they said to spin it. You have to know what it's spinning around. Otherwise, you're liable to get your image positioned incorrectly in the diagram. So we are going to need a given point of reference, and we're going to need to know how far to rotate the figure and in which direction. That means you are going to need to know that 90 degrees is like a right angle, 1/4 of a circle. 180 degrees, like a straight angle, is half of a circle. And of course, 360 degrees would be all the way around a circle, coming back to the original starting point. You also need to know the difference between clockwise and counterclockwise. So clockwise would be like if you started at the top of a circle and progressed to the right around the circle. Counterclockwise would be starting at a circle going to the left. So if you don't know the difference between clockwise and counterclockwise, you're probably going to need to spend some time staring at a clock, an analog clock, and learn that, because you will absolutely miss some questions going the wrong direction. Okay, so an example, rotate the capital A 90 degrees clockwise around the point. Okay. Now, sometimes the point that they provide can be external, like we are looking at here. It's not actually part of the capital A. And sometimes we'll see problems that actually give us instructions to rotate around a particular point where the point is part of the structure. So they could have like rotate the capital A by the apex up at the top of the capital A, spin it around itself at the very top, in other words. Anyway, rotate the capital A 90 degrees clockwise around the point. So we need to know 90 degrees, how much of a circle is 90 degrees? Well, hopefully from your vocabulary here recently, you know that 90 degrees is basically like a quarter of a circle. So that's 1/4 of the way around a circle, and clockwise would be spinning this guy around to the right if it's traveling from the top of a circle. So our capital A is traveling like a clock, and it's going to go 1/4 of a turn, okay, which is going to turn the A over on its side, with the apex of the A being towards the right side of the screen. And your pre-image has become your image, and your rotation is complete. Okay. Now, rotations cause people some problems. We have some difficulty understanding what the new object is going to be positioned like, how our image is going to be oriented. And a big problem that we have is trying to figure out where the point of reference is going to end up in our answer. So again, I have a strategy for you. Never miss a rotation. And the way that you're going to do this is to pin your point of reference to your desk, like using the eraser on your pencil, and then simply rotate the paper itself, not allowing the paper to move underneath the eraser of your pencil. Okay, so if we have the same instruction on a piece of paper, rotate the A 90 degrees clockwise around the given point. Okay, what we're going to do is we are basically going to pin down our paper. So you'd place your eraser directly on the dot right there, the point of reference, pin it down, and then actually rotate your paper. Physically rotate the paper 90 degrees clockwise around the given point. Stop wherever the amount of rotation tells you to stop, in this case a quarter of a turn. Now the exact way that you are looking at your capital letter in this case and the point of reference, all you need to do is make your answer match exactly what you're seeing right now. So if we copy down exactly the way we see it right now, this is what we see. We see the capital A, the apex pointing over toward the right side, the point of reference would be directly underneath the apex in this particular perspective. That should be our answer, whether we're drawing it ourselves or we're trying to match up a multiple choice answer. That's the way we do it, and it's done. So there's really no excuse to ever miss a rotation question or the positioning of the point of reference. Okay, now translation. Okay, translation is simply relocating an object. Okay, so if we're looking at an example, translate the Q down and to the right. Well, clearly there's not real rocket science going on there. We're just translating it down and to the right. Now again, we're going to be using these transformations for some more complicated things that we've never done before. Okay, so it's not as simply as just translating it down to the right, but you'll see what I'm talking about here in a few days. Okay, so we had our pre-image, we have our image, and that's pretty much it as far as translations are concerned for right now. Now, dilations are a completely different type of transformation. Okay, this one is not isometric, so it's not what we call an isometry, because obviously dilation, okay, dilations change the size of an object. Okay, so obviously we're not going to end up with the same size, same shape. The rate of change from the object to its image is stated by a scale factor. Okay, scale factor is a term that hopefully we already have a little bit of exposure to. It's going to be an idea that we're going to use quite a bit through our travels in geometry this year. And so we're going to make sure we understand how to read a scale factor. Now, scale factor is a ratio that tells how much a figure enlarges or reduces. Now, if you're not familiar with the term ratio, all it means is one number that is being compared to another number, and that can show up in a couple of different formats, and we'll look at those here in just a moment. Okay. All right, so let's take a look at a couple of examples on dilation problems. Let's say we're going to dilate this capital H using a scale factor of 1 to 2. Now that 1 to 2 with the colon in between them, that is one format possible for ratios. Okay, the first number that we are looking at, okay, is representative of information about the pre-image, while the second number that we're looking at is information relating to the image. So scale factor is written as pre-image to image if it's written in this format. If they happen to write it as a fraction, which is possible, the numerator represents the pre-image and the denominator represents the image. But scale factor is quite frequently written in with this colon notation that you see now. Okay, so basically what we're saying here, or what's being communicated to us, is that the image is going to be twice as big as the original, a 1 to 2 relationship. So when capital H is dilated, and usually they will make us move or translate our dilation so that we don't end up with two diagrams piled on top of each other. Okay, we can see that our capital H has basically become twice as big as the original, the pre-image, and then the image was twice as big. That's a scale factor of 1 to 2. Let's look at another one. Dilate the capital R using a scale factor of 3 to 1. Well, once again, the first piece of information represents the pre-image. The second piece of information in the scale factor represents the image. So we have a big number becoming a smaller number. That means our image is actually going to be reduced in size. Okay, and in this case, we're going to be looking at an image that is about 3 times smaller than the original. So the capital R, after it is dilated, we'll move it over so that we don't pile our examples on top of each other, and we end up with a much smaller capital R. There's your pre-image and your image. Okay, so dilations are not that tricky. It's just a little bit that you have to understand in order to work them accurately. Okay, now, different topic here. Objects can have symmetry if they fit certain characteristics. There's different types of symmetry. One of them would be reflectional symmetry. And we would say an object would have reflectional symmetry if a line could be drawn such that the object is the same on both sides of the line. Okay? Such a line, if one exists, is what we call a line of symmetry. An object could have one line of symmetry, it could have many lines of symmetry, or it could have none at all. It simply depends on what the object itself has to offer. Okay, so here are 3 various types of polygons. Okay, let's examine them one at a time for possible lines of symmetry. Now the one on the left, okay, this little block arrow looking guy, okay, if we look at him, I think most people would identify very easily that it does have a line of symmetry running vertically straight down through it. And that is a line of symmetry because it is exactly the same on the left side of the line as it is on the right side of the line. Examining the figure further, I think we'd probably agree very easily that that is the only line of symmetry that this shape has to offer. The hexagon in the center of the screen, however, has a lot more to offer. Now, obviously, it has that vertical line of symmetry just like the block arrow did, but on further examination, I think a lot of people would see right away that it could also have lines of symmetry running across from the other corner points of the hexagon. Additionally, some people will see pretty quickly that it could have a horizontal line of symmetry right through there. And then continuing to discuss and explore, we could probably see it through the opposing sides as well. Okay, so as we can see, this guy has several lines of symmetry. In fact, there are 6. Okay. It is shapes like the one on the right that tend to cause people problems, okay, trying to identify if we have any reflectional symmetry here. Now, a lot of people will say, oh, yes, it does. If you connect the opposing vertices, then what we have is reflectional symmetry running across like that. Well, let's explore that notion here just a second, and let's apply our idea of doing a reflection. Let's move the corner points that are not on this line of symmetry. Let's move them one at a time. Okay, so these green guys that I just marked in the picture, let's allow them to look into the mirror one at a time, and then see themselves the same distance out behind the mirror. And as we can see, what we end up with is we end up with 2 points that are actually not on the original figure. Okay, so this red line that we drew across there was a good idea, and it did kind of look like it might have reflectional symmetry there, but as we can see, it's not there. Okay, and if you're thinking, oh, well, what about the other direction? The other direction might have it. I think, once again, what you're going to see is that when the points look in the mirror, straight into the mirror, they're going to see themselves straight out the other side. And once again, we have points that are not on the original figure. So unfortunately, that guy was very tempting to say he had reflectional symmetry, but ultimately does not. There is also what's known as rotational symmetry. Okay, rotational symmetry would apply if a figure could be rotated so that the image looks exactly like the original before it completes a whole revolution. Okay, so for example, if we took something like this 4-sided shape, this quadrilateral, and what we would like to do is we'd like to discover, could I begin rotating this figure and have it realign with the pre-image before I complete an entire rotation? So let me grab a hold of this guy here. That's its original state. That's the pre-image. But as I start rotating, okay, do I rotate all the way around the figure before the figure realigns with its pre-image. And as you can see, it does realign so that we cannot tell the difference between the image and the pre-image. This is what is known as partial rotational symmetry, because it is realigning at times, but at other times it is not. Okay, so that does have some rotational symmetry. The last type of symmetry that we're looking at is called translational symmetry. Translational symmetry is a little harder to accomplish in a figure, and an object has translational symmetry if the image would realign with the object perfectly by way of translations. Now, this kind of symmetry only occurs in objects that have recurring patterns in them. So translational symmetry is actually pretty easy to predict by looking at a pre-image. If you can see a recurring pattern, then chances are you are looking at an object that has translational symmetry. So now the idea here is that if we were to reproduce this figure, and basically, hang on, I'm having a problem with my slide here. Okay, and if we were to realign the pre-image with the image, okay, as we can see, what we have is we have total realignment. You cannot tell the difference between the original figure and the new figure. Looks like my picture's having a little bit of trouble. Okay, but you get the basic idea. Now, true enough, you do have some squares or shapes that are outside of the original image now that are not aligning with anything, but we're just focusing on the overlap in between there. So what we are seeing is a figure that does have translational symmetry because the original is realigning with the image in a way that you cannot tell the difference between the two. So that is translational symmetry. Okay, that is it. I apologize for the length of the notes. It's always kind of tough at the beginning of the year because we do have a lot of information to convey. Okay, so write yourself a summary, and ladies and gentlemen, it's time for us to quit skipping the summary. I'm going to start not counting notes complete if you skip that part. So the video is about to end, but your work is not complete. It only takes you about 45 seconds. Look back over the information, write a sentence that kind of ties it all up and wraps it into a single sentence for you, or just two sentences for you. Scribble down any questions you might have that you need answering about this material, and keep in mind your essential question: can I recognize and apply the various types of transformations and symmetry?